Okay, the kinetic molecular theory applies to gases in three basic ways. First off, it says that the particles in the gas are tiny and they're relatively far apart, which means you can compress them. Gas particles are in constant, rapid, random motion. They generally truck along in a straight line until they collide with something, then they bounce off and go in some new direction. When those particles do collide with one another or with the walls of their container, the collisions are elastic. That means they're not static collisions. They don't stick together. They bounce off, and they conserve energy. So they don't really speed up or slow down. I mean, the total energy is going to be equal. So they're not, like billiard balls or pool balls. When you hit them and they collide, they slow down due to friction. Gas particles don't. Okay, so if a gas is compressed, what happens to the volume? Obviously it decreases. The temperature will also decrease. The pressure will increase. The number of moles of the gas particles will stay the same as long as it is closed off. The variable that has the greatest effect on average kinetic energy is temperature, because temperature is the measure of the average kinetic energy. So how fast they're moving, that's their temperature. Pressure is nothing more than the force exerted per unit of area. Okay, STP is standard temperature and pressure. These are the values associated with it. As far as temperature goes, 273 Kelvin or 0 degrees Celsius. Remember, as you're doing the gas law problems, all temperatures must be in Kelvin. Why? Kelvin has no negative values. Here are just some pressure units. These are the standard ones. 1 atmosphere, 760 millimeters of mercury, 101.3 kilopascals, 760 torr, 14.7 psi, 29.9 inches of mercury. This list is not all encompassing. I mean, there's other units of pressures, bars and so forth, but these will get you through most of the problems. Okay, the reason why gases can change volume easily and liquids and solids can't, if you notice in this diagram, the solid and the liquid, the particles are packed together about as closely as they can be. The gas particles, lots of room between them. That's why you can compress them. They also expand to fill their container. So that's what really differentiates the gases from the other two. When equal volumes of gas samples have the same temperature and pressure, the numbers of their molecules will be equal. What is true about the number of moles? They will also be equal. And what's true about their masses? They will vary due to their unique molar masses. Because each one of the gas particles has a different atomic mass, they will weigh different even though they have the same number of particles. They will be equal. This is a Boyle's law problem. How can I tell? It's measuring pressure and volume with no mention of temperature. So we're going to use P1V1 equals P2V2. The initial pressure is 105.2 kilopascals. Okay, and let's see, the initial volume is 250 milliliters. Okay, it looks like the final pressure is 100.3 kilopascals. I do not know the final volume. That's what I'm trying to solve for. How do I solve for x? Divide both sides by 100.3 kilopascals. Kilopascals cancel. So 105.2 times 250 divided by 100.3. The answer, 260 milliliters. Okay, this is a Charles law problem. How do I know? It mentions volume and temperature with no mention of pressure. So I'm going to fill in what I know. 125 mils of volume. I do not know the temp. The final is 128.6 mils. I do not, or excuse me, it's 26 Celsius, so that's 299 Kelvin. Yeah, 273 to it. How do I solve for x? Basically, you must cross multiply. So you end up with x equals 125 milliliters times 299 Kelvin divided by 128.6 mils. The milliliters cancel. 125 times 299 divided by 128.6. You're going to get x equals 291 Kelvin. Okay, this problem deals with the combined gas law because it has all three, pressure, volume, and temperature. So I'm going to start plugging in what I know. 712 millimeters of mercury is the initial pressure. The initial volume is 683 cubic centimeters. Okay, and let's see, the initial temp, it looks like 327 Kelvin. Okay, let's see the final pressure. It says it's 698 millimeters of mercury. I do not know the volume, that's what I'm trying to solve for. The final temp is 319 Kelvin. How am I going to solve for X? Easy, you cross multiply. So 319 Kelvin goes up here. The 698 millimeters of mercury go on the bottom. These cancel, millimeters of mercury cancel, Kelvin cancels, you're left with cubic centimeters. And so I'm going to multiply 319 by 712 by 683 divided by 698. And it looks like the final volume is going to be 680 centimeters cubed. As the pressure of a gas increases, the volume decreases. This is an inverse relationship. As one thing gets bigger, the other gets smaller. The formula associated is Boyle's law. P1V1 equals P2V2. As the temperature of a gas increases, the volume of the gas also increases. This is a direct relationship. The formula associated with this is Charles' law. V1 over T1 equals V2 over T2. Okay, here are a couple of quick sketches that's relating, let's see, the first is gas volume and pressure. So basically, as volume increases, pressure decreases, you have a negative slope. If you look at the next one, as volume increases, temperature also increases. And so which one is a direct? A direct one is the one where both things do the same. This one is the direct proportion. And then this one is the inverse, so as one goes up, the other goes down. Okay, this is an ideal gas law problem, so I know the initial pressure is 1.11 atmospheres. I do not know the volume. I do know the number of moles, 0.056 moles. I do know the gas constant has to be 0.082 atmosphere liter per mole Kelvin. And then 25 Celsius, 25 plus 273 is 298 Kelvin. How do I solve for this? Divide both sides by 1.11 atmospheres. Moles cancel, atmospheres cancel, Kelvin cancels, we're left with liters. Multiply, 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 and divide, and you end up with 1.2 liters. Here's another ideal gas problem. Going to plug in what I know. 88.4 kilopascals. Let's see, I do know the volume in this case. You do have to convert the volumes to liters using the ideal gas law. Why? Because of the R constant. It has whatever unit in liters in it. We do not know the number of moles. This time the value I need to use for R is 8.31. Why? Because it's kilopascal liters per mole Kelvin. And then 85 degrees Celsius is 358 Kelvin. Okay, so how am I going to solve for this? I'm going to divide both sides by 8.31 kPa liter per mole Kelvin, and then 358 Kelvin. These go away. The moles stay. Kelvin cancels, kilopascals and liters cancel, so we keep the moles. I multiply and divide, and you end up with 0.0102 moles of carbon monoxide. But it didn't ask for moles, it asked for the mass. So this is just normal stoichiometry now. I know for every 1 mole of carbon monoxide it has a mass of 28.01 grams. Moles cancel. Multiply, you get 0.286 grams of carbon monoxide.